There is something deeply unsettling about what the latest images of 3I Atlas reveal. When astronomers pointed the Hubble Space Telescope toward this interstellar object, they expected irregular dust, messy outgassing, and the familiar disorder that defines natural comet activity. Instead, they found something that immediately stood out as wrong in a very specific way. Emerging from the nucleus are two narrow, sharply defined structures extending in opposite directions with striking balance. They are symmetric, persistent, and clearly structured. Most importantly, they are not aligned with the antitail, not shaped by sunlight in any obvious way, and not behaving like the diffuse, chaotic features seen in normal comets. These are jets, but not the kind astronomy is comfortable with. Stable over time, mirrored with precision, and resistant to simple explanations, they force a difficult question into the open. Can something this orderly truly be natural, or are we missing a fundamental piece of the physics at work? 3I Atlas is not from our solar system. Its trajectory, speed, and origin mark it as an interstellar visitor, a rare category of objects that pass through our cosmic neighborhood briefly before vanishing back into deep space. Objects like this are expected to be extreme, but not orderly. They are relics from other stellar systems, shaped by unfamiliar environments, battered by time, and assumed to be physically rough and chaotic. When astronomers first began collecting data on 3I Atlas, they anticipated oddities related to speed or composition. What they did not expect was geometry. The Hubble images show a bright central nucleus surrounded by a diffuse cloud of dust and gas, a coma that looks familiar at first glance. But emerging from this coma are two thin, elongated features extending outward in opposite directions like arms. They are not wide, fan-shaped dust trails. They are not fuzzy or dispersed. They are narrow, structured, and surprisingly clean. Most importantly, they are symmetric. This is not the kind of symmetry usually seen in cometary activity, especially not in an object that has never before passed near our sun. In natural comets, jets form when sunlight heats surface ice, causing volatile materials to sublimate and escape into space. These jets are typically uneven. The surface of a comet is irregular, fractured, and heterogeneous, meaning some regions activate while others remain dormant. As the object rotates, different areas are illuminated, producing jets that turn on and off, curve, and change direction. The result is disorder. Even when jets are present, they rarely balance each other in shape, brightness, and direction. Symmetry is not impossible, but it is fleeting, unstable, and rarely sustained. What makes the case of 3I Atlas notable is persistence. The symmetric features appear in multiple images taken at different times. They are visible not only after heavy processing, but also in raw data once one knows where to look. They maintain roughly equal length and brightness on both sides of the nucleus. They do not drift, bend, or dissolve in the way dust structures normally do. They do not align with the antitail, the phenomenon caused by dust particles spreading along the object's orbital plane. They also do not point directly away from the sun, which would be expected if solar radiation pressure were the dominant shaping force. To confirm that these features were not artifacts or illusions created by image enhancement, astronomers applied a well-known analytical method called the Larson-Secondina gradient filter. This technique suppresses the bright central coma and enhances faint directional structures, allowing subtle features to stand out. When applied to the Hubble images, the result was unmistakable. Two narrow structures emerged clearly, balanced on opposite sides of the nucleus, extending outward with measurable length and coherence. These were not random noise patterns. They appeared consistently across multiple exposures and observation dates. The geometry of these structures suggests something closer to jets than tails. A tail is diffuse, shaped primarily by external forces like sunlight and solar wind. A jet, by contrast, is a collimated stream of material originating from a localized region on the surface. Jets imply directionality. They imply source regions. In extreme cases, they can resemble thrusters, although no claim is made that this is what is happening here.
Now, as of this morning, some observers noticed that it has a set of jets around it, more than 7. Some headed towards the sun, some away from the sun.
Still, the distinction matters. Jets point back to processes occurring at or below the surface of the object itself. One natural explanation proposes that 3I Atlas has two active regions positioned roughly opposite each other, possibly near its rotational poles. If the object is spinning and these regions remain continuously illuminated or periodically activated in a balanced way, they could, in theory, produce symmetric jets. This scenario requires a very specific alignment of rotation axis, surface composition, and thermal behavior. It is not impossible, but it is statistically uncommon, especially for an interstellar object whose formation history is unknown. The difficulty with this explanation lies not only in the symmetry itself, but in its stability. In most comets, jets vary in intensity as rotation exposes and conceals active regions. The jets of 3I Atlas, however, appear unusually steady. Their shape and orientation do not fluctuate dramatically over time. This suggests a controlled or constrained physical process, one that resists the normal variability seen in natural cometary activity. That alone is enough to raise eyebrows within the scientific community. Context matters here. The symmetric jets are not an isolated anomaly. They join a growing list of features that have made 3I Atlas difficult to categorize. Observations have suggested that the object's rotation axis may be unusually aligned relative to the Sun. Gas emission velocities appear slower than expected for standard sublimation-driven activity. The anti-tail has displayed an unusual narrowness and persistence, appearing in ways that challenge conventional models. Each of these features taken alone might be explained away. Taken together, they form a pattern that resists simple dismissal. Comparisons with earlier interstellar visitors deepen the mystery. The object 2I Borisov, observed in 2019, behaved much more like a traditional comet. Its jets were messy, irregular, and dynamic. Its coma evolved in predictable ways. There was nothing about Borisov's appearance that suggested geometric organization. 3I Atlas, by contrast, seems to favor order over randomness. That difference is striking, especially given that both objects originated beyond our solar system. This does not mean that 3I Atlas is artificial, engineered, or controlled. No credible scientist has made such a claim. Even those who openly discuss the anomalies emphasize caution. The presence of symmetry does not imply intent. Nature is capable of producing structured outcomes under the right conditions. Crystals are symmetric, magnetic fields are organized. Planetary rings can be sharply defined. The issue here is not whether symmetry can exist, but whether the known physical processes governing small icy bodies can plausibly produce this particular kind of symmetry in this particular context. One possibility is that the internal structure of 3I Atlas is far more ordered than what we are accustomed to seeing in small bodies from our own solar system. Instead of a loosely consolidated mix of ice and dust, the object may be internally layered, with volatile materials arranged in a way that channels gas release along preferred directions. If those volatile-rich layers are positioned symmetrically with respect to the object's rotation axis, the result could be two opposing outflow regions that activate in near-perfect balance. This would not require intelligence or intent, but it would require a very specific internal geometry, one that resists fragmentation and maintains coherence despite thermal stress. Such an arrangement would be rare, but rarity is exactly what we expect from an interstellar object that formed under conditions we have never directly observed. Another possibility lies in the object's surface history. 3I Atlas did not form near our Sun, and it did not evolve under the same thermal cycling that shapes comets in the Kuiper belt or Oort cloud. Its surface may have been sculpted by a completely different stellar environment, one with higher radiation levels, stronger stellar mins, or a different balance of chemical elements. Over long periods, this could selectively harden some regions while preserving volatile pockets in others, creating stable, long-lived vents rather than transient, chaotic outgassing sites. Collisions in its home system or tidal interactions with planets or stars may also have contributed to shaping its structure in ways that promote symmetry rather than randomness. Interstellar space itself adds another layer of complexity. The journey between stars is not a passive one. Objects traveling through the galaxy are exposed to cosmic rays, background radiation fields, and gravitational perturbations that differ significantly from what small bodies experience inside a planetary system. Over millions or billions of years, These influences can alter surface chemistry, drive internal compaction, or preferentially erode weaker regions. The result could be an object that appears oddly disciplined in its behavior once it encounters a new star, responding to solar heating not with chaotic disintegration, but with controlled, repeatable activity. Even with these possibilities on the table, the symmetry remains difficult to dismiss as mere coincidence. Symmetry is demanding. It does not arise easily in systems dominated by irregular shapes, uneven heating, and stochastic processes. It requires constraints that limit variability, mechanisms that reinforce balance, and conditions that suppress the noise normally present in natural systems. In astronomy, sustained symmetry is often a clue that something fundamental is guiding the behavior of a system, whether that guidance comes from gravity, rotation, magnetic fields, or internal structure. When astronomers encounter such symmetry, their instinct is not to speculate wildly, but to search for the stabilizing process that makes it possible. What happens next will depend on continued observation and careful modeling. As the object moves through and eventually out of our observational range, data collection becomes urgent. Each new image adds another constraint, another piece of the puzzle. Even if a fully natural explanation emerges, it will likely expand our understanding of how small bodies behave under extreme and unfamiliar conditions. The key point is not whether 3I Atlas is extraordinary in an absolute sense, but whether it forces us to refine our expectations. Interstellar objects are rare messengers. They carry information not only about their own composition, but about the environments in which they formed. If 3I Atlas is telling us that symmetry and stability can arise more readily than we thought, then that lesson alone is valuable. For now, the balanced jets remain. Quiet, narrow, persistent. Not dramatic in motion, but profound in implication. They do not shout answers, they invite questions. And in science, that is often the most important contribution an object can make.